Session 3 and 4 taught by Dr. Reams and Black in 1977. This is tape 18 side B.
2. Well, the lowest denominator on that one is 1. For instance, suppose that you had a 64. Now, you wanted to know this, no, hold it, not the logarithm, but you wanted to know the square, the minus square of 64. What would it be? It would be 8. That's right. Now, it would be a minus 8. Now, what is the square of that? Yes. 8. Now you want to convert it to its log, which would be 1.4. Right. But you lower it up here in a big number. You want to lower it down as far as you can before you make a log out of it. Yes, either going up or down. One is minus going down and plus going up. Let me give you another one now. Let me just give you another one. I'm afraid to give you another one. I'm afraid to confuse you, but in the midst of confusion, there's progress. For instance, suppose that you had, we'll say, 4 to a minus 4 power. Now, what would you have? What's that? 1 over 256. That's what you'd have. Only be a minus. Minus 1. Now. Why would it be a minus? Because you had a minus up here, but it's your minus 1. So as your 1 doesn't have any power, you can forget about your 1, and then your log here would be 127 plus, because this is a plus down here in relative math. It's only a plus, it's only a minus on your 1 because it's on the opposite side. This is not a division like you have you're not dividing like you have. This is not a division sign at all. This is correct.
Dr. Reams,
yes.
You could write out the answer now. In other words, this equals what? Does it equal 1.27? Does it equal 1 over 1.27?
No. You throw away the 1.
So it equals, put an equal sign after it. 1.27.
It isn't an equal sign. The 4 to the 4th power and a log is 127.
So that's the answer.
That's right.
That would be the next.
Well, that is with a minus up here. With a plus, it would be, if you had a plus up there, you would have a 256 and a 2, be 1. So 256. Here's the difference. One is that you're gaining energy, and one is that you're losing energy. Now, as far as your logarithm, you don't know in biological math which you're dealing with, except by your numbers and your table, of which we will take up tomorrow afternoon when we describe the patient.
What atom would that represent? That's 4 to the minus 4.
You can take any atom you want to, any element you wanted to. Any elementary atom. We're dealing in elementary atoms only this afternoon.
Okay, so is the 4 the atomic weight of a substance like helium?
No, helium. Yeah, 4 is helium. 4 is helium, yes. That's right. Well, if helium, like all elements, is exposed to oxygen, it gives off what? Ions, right? And therefore it would be a minus, but Suppose that you were collecting, manufacturing, taking helium out of the air, then you would have a plus. It would be an increase at the same ratio of an increase as a decrease. Clear? In other words, the plus is that you're gaining and a minus is that you're losing here. That's the difference. Now, this is in your math of one atom. Now, for instance, radium, 1 gram of radium will completely evaporate in an hour and a half. It'll give off all its anions and not be in existence anymore. Completely, all of its cations at least, give off all of them. Only it'll give off its cations in anionic form. Did you realize, you see what I'm saying?
Are you talking about half-life?
What's that?
Half-life? Of the radioactive substance?
Yes,
You are.
yes. So, trying to put it together, we're trying to get you the vision, the clearness of what the purpose of logarithms is, to express large numbers. Now I'm going to go into a complete different angle of it at all and show you why. Now, if there's 10,000 drops, M equals 1,000 equals 1 pound. And the body weighs, we'll say, weighs 100 pounds. Then you've got, what's that? So 10,000 drops. So you've got 10,000 drops equal 1 pound. No, 1. 1 to the 6th. You got 6 zeros. 1, 2, 3, 4, 5, 6. 1 to the 6th power would express then the number of drops. Now, suppose you multiply that then.
Doctor, is it multiplied to 10 million times the 100 pounds? The 10,000.
That's right. 10,000. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, 1 from the 10, yes. 4, 5, 6. That's correct. This is correct. Now, you've got, we're dealing in 1 pound now of water. This is water we're dealing with. We're dealing in 1 pound of water, 10,000 drops of water. 6 zeros. Count your number of zeros, and that's all it means. Yes? You could do that very well if you wanted to, but then that's a lot of extra work. There it is, expressed differently, but for short, we just say 1 to the 6th power. It's exactly the same thing. This is why you need 3 or 4 months study, at least, or even 6 months on logarithms, because it's impossible for me to explain logarithms in 2 hours or 4 hours. What? Just a moment. What?
Now that you've written it out, I can see where the two parts, visually I can see them, but if you take 1, as we did when you first started with us, 2 squared and 3 squared, we took the number and multiplied it by itself. 2 squared is 4, 2 times 2, and so forth. Is there a way of explaining how 1 to the 6th power, instead of being 1 times 1 times 1 times, and so forth, is really 1 times 10 to the 6th power?
No, we're dealing with 2 different logarithms that's in the book here. We're doing two different types of problems that's in your logarithms. One is dealing with powers, and one is dealing with units. This is a unit, and dealing with your units. But wait, before we ask any more questions, let me finish right here what we're doing, and probably I'll answer your question. Now, we've got 1 to the 6th power gives us then the number of pounds, the number of drops and 100 pounds of water, yes. But now, water, then times water, H2O, this is a plus, this one would be a plus, and it would be 16, and this would be 2, it would be a total of 18. It would be 1 to the 6 times 18. So that to the lowest denominator is 1.8. Okay? Yes. I agree with you 100%. That's why I recommend 3 months difference between. But I'm going to tell you this. I don't care how much of a wizard of a teacher you got. You can't get in 2 hours. If they understood what I'm covering this afternoon, then I wouldn't need to cover this. I would just merely hit through it in a matter of 15 minutes and then start right on the problem.
That can be done, is what we're saying.
What's that?
That can be done.
This is why I'm saying you need 3 months at least between these classes to learn this. What?
You don't need 3 months.
Well, I'm going to tell you, friends, I studied logarithms 2 years before I could really handle them like I do the multiplication table. I understand. I had it in high school and about 7 or 8 years of college, too.
Dr. Reams, what we mean is that you are so much above us in these concepts that you cannot come down to our level to lift us up, so we need sort of an intermediary that sympathize with our ignorance and lift us little step by little.
Is there anybody here that can make it more simple? I'm certainly willing to listen, and the man that helped me did a fabulous job a few minutes ago. But I do not know how to make it any more simple than I'm doing. If you can help me, anybody can help me to explain it to you in terms, I would appreciate it, because I do not know how to make it any more simple.
Question, Doc.
Yes.
That 1 to the 6th power you got over here on the side, that is actually 10 to the 6th power, isn't it?
No. In relative math, you do not deal with zeros. Please remember that rule. Don't forget it. This is relative math. This is geometrical math. See if you can help me, because
I understand. Yeah, I don't know now. You mean from up here?
Yeah.
Okay, what does M mean? How many are there in 100 pounds?
A million.
Okay. Pardon? Okay, but then he's breaking it down here, see? I'm poor at this. This one here? This one here, okay. Well, I want to use what figures he has here so that you understand that. But you understand this point and how he got the 1 million here, okay? Then all he's doing is breaking this down into a number that's easy to work with instead of working with all the zeros, okay? But again, if you change it to relative math, then it's 1 to the 6th. You see, the problem is you've got to have a little bit of background in math to see the symbolism. Just like you look at this dot here. Some of you may not even know the dot means times. You see? And
Where you got the 6?
where you got the sixth? Okay. That's why I said this earlier. If you want to express a large number in exponential terms, you take it. Okay. If you take the number 1,000,000 and you want to express that in easy, what we call exponential terms, you merely count the number of zeros, which is a decimal place. If this is decimal 00 up here, you move it over that number of places. And how many zeros are there here? Okay, that's 10 to the 6th. 10 times itself will equal 1,000,000. And all you would say here is 1.0, but you don't even need that. And what Dr. Reams is doing is canceling this off in relative math and saying 1 to the 6th. And that's all that means. It's just have to understand that symbolism.
It's not easy. It's a rule.
See? Pardon?
That's his definition of what's accepted.
Right, that's what I'm saying.
That's the rule that's in the book.
If you look at a standard log table, which it would do well for you to probably look at one and understand it, they'll have it listed. Let me show. Can I just see the one that's in there so I can?
I just want page 257, I believe.
If you wanted to calculate the miles per gallon in your car, and you calculated it out as 31.634582, you know, would that decimal point be important to you? It's relative, isn't it? Who cares? If you're familiar with the symbol pi in mathematics, what does pi equal? 3.14. How many points can you carry it out? What does it matter? All you're concerned about is 3.14. It'll still come close to what you want to work with. That's relative. You know, you've heard the people say, "Oh, that's relative." It's not that important to go that far. So that's what we're doing here and expressing it. I just wanted a log table, just a table on the back of the boat. Yeah, just so that they could see it. If you look at a log table,
This is what we're doing with the end.
okay, we're dealing with are just base 1. That means that anything times the 1 times any number is the number, right? Okay? We're not trying to break it down into anything more than that. So if you look at a log table, you'll have n, which is the constant here, and you'll have 0, 1, 2. You've seen these mileage maps where you can look at San Francisco and Los Angeles and you map down across and you find the number. You've seen those? You understand me? Okay.
That's a mileage log.
Yeah, that's a mileage log, right?
That's right.
Okay. You have 1.1, 1.0, 1.1, 1.2, and then this across here are decimal points. Okay? And this one here, of course, 1 times 0 is what? 0. 1 times itself, the log of that number is 0.43. On 2, it's 0.086. Okay? If 1.1 times in the 0 exponential form is 0.414. Well, this is off the chart. That's where I'm getting this, okay? I'm just trying to illustrate something here.
301 power is equal to 2. Therefore, the logarithm of 2 base 10 is 0.301.
Right. Okay, exactly.
This is in geometrical math.
Right, it's in geometrical math. Okay, it's base 10 in geometrical math. I'm sorry. Okay? You understand? Again, that's where we come back to here. This is relative math. In geometric math, it'd be 1.0 times 10 to the 6th, or you could just say 10 to the 6th. Okay? Well, I mean, this is geometric, and this is relative math expression. Okay?
That's correct.
Okay.
What they've got to do in that there's more than one way to express any.
Yeah, all right. Now I'm trying to figure out where you want to go from here.
Just explain how
Dr. Reams,
Yeah.
I think it would be very advantageous at this point, since many people knew very little about logs at all, to establish what the logs were in base 10 to the
Okay, come up and do it for us. Come up, that would be a help.
Going to stick with the geometrical math to establish a basis from which to work, and then we can jump maybe to where Doc is thinking, all right? Common logarithms have the base 10. Now, 10 to the first power in geometrical math is equal to 10. The symbol up here called an exponent, which is also a logarithm. An exponent is another name for logarithm. Logarithm is a Greek word which means something the number as it should be. If there are any Greek students, maybe you can correct me on that for the exact. This is nothing more than a shorthand system at this point. This number, the exponent or logarithm, is simply telling us how many factors of 10 we have. Now, what is a factor? It is one of any number of numbers multiplied together. For example, 2 times 3 times 4, there are 3 factors there. X is meaning multiplication in this case. Now, if we have 10 squared, what we're referring to is 2 factors of 10. So this equals, in geometrical mathematics, 10 dot, I prefer not to use a dot because it's easily mixed up with decimal point, but I'll use it. 10 times 10. 10 to the 7th power is 10 times 10 times 10 dot dot dot, so we've got 7 factors of 10 written out there. Are there any questions as to what the exponent means? All right, now let's go on. Expanding the idea. 10 to the first power equals 10. 10 to the second power equals 10 times 10, or may I jump to 100? Listen, after you've taught high school and college for 16 years, you realize to check and find out where you are. 10 cubed, if I may, is 1,000. Notice here, children. God told us if we wanted to enter into the kingdom of heaven. All right? Notice the relationship between the exponent and that. I'm going to keep that a mystery. Only some of you saw it. Notice this one here, and look, that, and that. Ten to the 4th power. Now somebody guess what we're going to write down here. How many zeros, which we will disregard later, must I write now because we're in geometrical math? All right. Now we're going to make a huge leap in abstraction, if you're ready for this. Between the number 100 and 1,000, there is an infinite number of values. If we can represent 100 by 10 squared and 1,000 by 10 cubed, then there must be some way in this little shorthand method we have up here of expressing the numbers that are in between. For example, what would be the expression in the left-hand side for the number 200, let's say? Your common sense, maybe not, some sense would tell you that it must be that the number up here is between what? 2 and 3. Okay. I realize how low that's hitting. Okay, so it must be 2 point and some more then. Okay. All right. Just don't let us go too fast. 200 is between 100 and 1,000. Then the number 200 as it would be, okay? Everybody okay? All right. Now we look in the back of the book here, and I'll call on Hewlett-Packard for this, it's faster. Okay, 200 and if you have a good memory, you'll remember what it is from the, right, now you're getting it. I got to get some more places fixed on this. It's got to be 2.3010. Have you ever seen that before? A few minutes ago, when he took it out of the table, the 3010 came from one of those columns. In basic logarithms, we call the whole number portion of the log the characteristic, and this portion the mantissa. In other words, actually, this is not a table of logarithms. It's a table of mantissas. You have to learn to calculate the characteristic yourself, which is quite simple because any number between 100 and 1,000 has a whole number portion of the log of 2. And any number between 1,000 and 10,000 has a whole number portion of 3, etc. And so the table in the book, when you're studying at home before the next class, is simply going to give you that portion, or the mantissa portion of the logarithm. And that's all there is to it. Now I'll duplicate some of the table here in the book. He had started at this point now, which I think might have confused some of you. The column which is labeled small n stands for any number that you want it to be, except that you have to read what's there. For example, I'm going to go down to 1.5. Now that could be 1.5, or that could be 15, or that could be 15 million. It makes no difference. You are going to compensate for that simply by the fact that when you write the logarithm down or think of the logarithm, you write the characteristic that belongs there, depending upon which number you want. Now, if we had no columns across here at all, then you could only get logarithms of the number 1.5 or 15 or 150 or 1,500 or 15,000. But they've been nice to us and gave us other numbers. Now, let's fill this in because we would have to have this one here. And they will give us some number, in this case, 0.1761. Now we have a column here labeled 1. So we're able to find the logarithm of any number sequence 151. Put the decimal wherever you want. But when you write the log down, you have to compensate by putting the characteristic in properly. So 151 number sequence is 1790. All right, question. You write down on your paper the log of 1510. What is the logarithm of 1510? Okay, here's a short way to do it, isn't it? Count how many digits you have here before the decimal point. There's 4 of them. Knock one off, and that's 3. Or we can relate it to scientific notation. Now watch this. Take this number, write it in what we call scientific notation, and you have 1.510 times 10 to what power? The third power. There's the characteristic in, yes, there's the characteristic in the logarithm. It's 3 point, and at this stage, you look in the table now and find the mantissa, 1790. What does that all mean? It means that 10 raised to the 3.1790 power. Now that's an exponent. It's also what? A logarithm.